Greetings. This is Math Econ 464 from Hillsdale College, and we're continuing with our discussion of the economic uncertainty and how we might model that. And of course, we're using expected utility as our approach for this. Today, what I'd like to do in this lecture is discuss how expected utility can be used to model insurance. This is the kind of thing, this is the background that we used when I was in consulting and we were working on crop insurance. This is exactly the kind of approach that we had and the way that one conceives of insurance. So this has application. It'll have application in graduate school. If you go into actuarial work, it has application there. And this is a pretty generic kind of an approach we're going to take. I'm going to start out with a generic insurance problem, and this will be a simple case. We're going to have we always say simple. And if they say simple model, usually that means the mathematics is very hard, but the assumptions are simple. This is really a simple case in which assumptions are simple, and actually the mathematics is not very hard either. But we'll have two states, and that's either accident or no accident. And we're going to assume that let's make it a homeowner. And so it's homeowner insurance, and it's insurance against a fire. That's our disaster. The either accident, no accident, and the von Neumann-Morgenstern risk utility maximizer will be risk averse. And again, that means that this person has diminishing marginal utility of wealth. And so let's go ahead and set up our model, and we'll see what we come up with. And so our generic problem is going to have, let's start out with a completely clear board. Let's define the initial wealth of the homeowner as W. That's the initial wealth of the homeowner. And this is the person who is a von Neumann-Morgenstern utility maximizer, has a von Neumann-Morgenstern utility function, and is risk averse. That is, it will have that concavity, diminishing marginal utility. Secondly, we'll have the probability of an accident. So we'll say the probability of a fire, we'll make it a fire, is simply P. And P is, of course, greater than 0 and less than 1. The amount of a loss, if there's an accident, is L. Loss if there's an accident. So the final wealth in that case would be W minus L. And Q will be the quantity of coverage purchased. Quantity of insurance coverage that is purchased, that's what they're going to choose. That is to say, if there's an accident, that's what the indemnity that the insurance company will pay will be. Great. I hope that we're on. I think that should be visible there. Great. All right, good. So Q is that's in other words the amount of the indemnity paid if there's an accident. Okay, great. And finally, there's the insurance premium on a per dollar basis, and that would be the insurance premium is the amount of cost of a dollar of coverage. Great. So here's the question that we're setting up. The homeowner is going to try to decide what quantity of insurance to purchase, and each dollar worth of coverage will cost pi. Great. And so let's set up the lottery over here that will be facing that homeowner if insurance Q is purchased. So the lottery, which I'll describe this way with a little cursive L, that lottery is equal to the set WL. We're first going to describe the two states and then the probabilities. And the two states are, they will start out with W. This is what happens if there's a fire. W minus the loss plus the indemnity that they get because of the fire, and then minus pi times Q. That is the cost of that Q dollars worth of coverage. Great. And then the other state is there's no fire, W, their wealth, minus the cost of the insurance. And then that's not a J, that's a semicolon to show that next we're going to talk about the probabilities. The probabilities of each of those states is P and 1 minus P. Great, so there's our lottery. And that right there is, that is the wealth if fire, and wealth if no fire. Hopefully that green shows up on the camera. And there's the respective probabilities. Probability P, 1 minus P, that's our lottery. Great. So then we can think of what the expected utility of that lottery would be. And the expected utility would be, the utility of lottery Q is simply equal to, and I'm going to get that out of the way so I've got space to write, and that would simply be equal to P times the utility in case of a fire, which is U of W minus L plus Q minus pi Q plus von Neumann-Morgenstern utility maximizer, so it's additive, and that would be that times U of W minus pi Q. All right, great. Now, the goal here is to choose Q to maximize this thing. Okay, this is the decision problem that is facing the individual. Great, so let's take a look at what those first order conditions, what the first order condition would give us. And we'll put that over here. So as you know, the first order condition, that first order condition is going to be a necessary and sufficient condition by virtue of the concavity. The concavity, that utility function, also means that the second order condition is satisfied here. So this will be for an optimum, for a maximum. The homeowner's first order condition will be that du dq will be equal to 0. And that comes to, if we take a look at this, well, we'll take it with respect to that, that'll be P times 1 minus pi, P times 1 minus pi, and then U prime using the, the chain rule, and U prime of W minus L minus plus Q minus pi Q. And then we've got to run out of space, so we'll put this on the next line. It continues. And I'm going to put a minus here, as you'll see why in a second. 1 minus P, and that's pi, and then U prime of W minus pi Q. We set that equal to 0. And of course, that's minus because that would have been, when I took the derivative of this with respect to Q, I get the minus pi. So I just brought that out and then transferred the minus, the negative 1 over here, multiplied it. Great. Excellent. Set that equal to 0. And then, with a little bit of manipulation, what I want to do is to simply take this side Actually, we just want to move this side over to the other. And so this gives us, in other words, P times 1 minus pi U prime of W minus L plus Q minus pi Q. That is, subtracting out the amount they paid the insurance company, the amount they received from the insurer, the amount of the loss, the initial wealth, will be equal to this, 1 minus pi, 1 minus P pi U prime, and W minus pi Q. Great. Can we interpret this? Well, this is the expected marginal utility if a fire occurs times the share of $1 spent on premium that is then returned to you. That's the share of the dollar spent on premium that's returned. For every dollar of premium, you spent pi, and you get that back, okay? And that's the marginal utility of it. And the expected marginal utility of that, we could think of that as being the marginal benefit of insurance. And if we don't get fire, what do we get? Well, we have the expected marginal utility if no fire, the expected marginal utility if there's no fire times the cost of $1 of insurance. So that, in a sense, could be thought of as a marginal cost of insurance. And so that's what we've worked out so far. Makes a kind of sense. In fact, let's manipulate this a little bit more so we can interpret it further. And gathering our terms so that we get the pi's and the p's on this and this on one side, and then the utility, the marginal utility expressions on the other side. We'll simply divide both sides by this and divide both sides by this, and we get U prime W minus L plus Q minus pi Q over U prime of W minus pi Q is equal to 1 minus P pi all over P 1 minus pi. Great. So what do we have here? That's the marginal utility that we have in event of an accident or a fire versus divided by the marginal utility of no accident, no fire. That will be equal to the expected value of the cost of $1 of insurance when there's no accident versus the expected benefit of a payout if there is an accident. Great, so that's analogous again to the usual kind of first order condition that we get, say, with a consumer budget problem, okay? All right, good. Well, there's that comes from that's the insurance purchaser's problem, the consumer of insurance. What about the insurance company? What about their lottery? So next, to solve this problem, to work on this, we have to work with the insurer. And from the insurance company standpoint, we'll have to have a couple of assumptions. But we'll start out with the insurer's lottery. And we'll call that one, I'll just call it LF for the firm. Their lottery, with respect to this, is equal to pi Q minus Q. And what's this? This is the payoff to them if there's a fire. They receive the payment from the insured, and then they have to pay out the indemnity. And then if there's no fire, they simply get pi Q. They don't have to pay out an indemnity, and the probabilities respectively are P and 1 minus P. Chance of a fire and chance of no fire. Great. All right. Now we have to have a couple of assumptions in order to work with the firm. And assumption number one is that they are, assumption one, risk neutral. Risk neutrality is generally what we do with firms, not always, but typically you would assume a firm is a risk-neutral von Neumann-Morgenstern utility maximizer. That is to say, the utility function the von Neumann-Morgenstern utility function will be linear. Now that's not always imposed, so especially you think of small companies that might be risk averse, but we're gonna assume a big company, it's a big risk-neutral insurer. We can justify this because if they're insuring independent risks, you should know that if you combine enough independent risks, you get a smaller variance, and the risks will diminish overall. Great, so we're going to assume risk neutrality. Therefore, the utility for the firm will be given by, we will simply say P times pi Q minus Q. So we can just treat them as if they are expected wealth maximizers. And because they won't have any marginal diminishing or increasing marginal utility of income. It's constant. And then pi Q. Okay, so there's their utility function. All right, great. The second thing we're going to assume, and this is a really important one if you get into a PhD program, we're going to assume that this is a competitive market. A competitive market, well, let's write that down. What does that mean? Assumption 2 is, we'll say, perfect competition. Perfect competition means that we also know that the utility, or in other words, the profit for the firm is equal to 0. Okay. This is the perfect competition, and this is the risk neutrality here. Okay, great. Put too many marks in here. All right, good. And so now we're ready to work on this a little bit. And so let me get a little bit of space to work. And the first thing we'll do is start solving this. And what that tells us then is that this must be equal to, I'll do this step by step. P pi will multiply through P pi Q minus PQ plus, let's see, pi Q, and then, is that right? Yep. And then finally, oh yes, P pi Q minus P pi Q equals 0. Okay, great. So I'm not even taking first order conditions here. I'm simply solving this thing. And I find that then, let's see, we have plus, minus, oh, this is really simple. It looks like I've got, that must be, what is it? Pi minus P Q, since that's a negative P and that's a plus pi and they're both times Q, that simplifies to this and those things are gone, equals 0. And that's true for all Q not equal to 0. And therefore I know that pi equals P. Yeah, so what? That is an important principle that we call, it's called actuarial fairness. And that should hold given the assumption of a competitive market. Actuarial fairness, and what does that actual fairness means? It simply means that the premium equals the expected value of the indemnity. Okay, great. The total premium will equal the expected value of the indemnity, actuarial fairness. Great. So now you know what the insurer is going to charge. So we can go back to the consumer and solve this problem further. What did we have for the consumer? We worked down to this point, but we now know that P and pi are equal. And so let's go ahead and, how did I want to change those? Well, we know that that's then equal to 1 minus p over 1 minus pi over p. And since those are all equal, 1 minus, oh, cool. It looks like that's a 1, and that's a 1, and that's equal to 1. That is to say, those will be equal to each other. Okay, great. Let's go ahead and try to set that up. So we now know that the marginal utility in each possible state will be the same, W minus L plus Q minus pi Q is equal to U prime of W minus pi Q. And so now we can further solve this. That must mean that Q is equal to L. That is to say, full insurance. If we have actuarial fairness. Faced with the risk-averse consumer, faced with actuarially fair insurance premium, will buy full coverage against the loss. Great. Let's take a look at that graphically and just see what this might mean. And so we'll clear this. Get a little bit of space to draw a graph. And we have utility on this axis for the consumer, and we'll put wealth on this axis for the consumer, and we'll draw our von Neumann Morgenstern utility. There's utility of wealth. And here's the wealth if there's no fire. So this is their starting point. And that would give us this level of utility. There's U of W. And don't worry too much about that because we're not going to do much with it. But then we've got wealth if there's a fire, and we'll just move that down here. And that's the uninsured wealth if there's a fire. Great, so they're here. And then the lottery they face will be something like this. It'll be along some combination along here, depending on what their, the risk of a fire is. And so let's say that given risk of a fire, that would put us right here would be our expected wealth. That is, in fact, wealth at fire. Let's just call it by what we were, W minus L. So that's P times W minus L plus 1 minus P W. And that puts us to right there. And that would give us, that would be the expected utility with no insurance. The utility of no insurance, and then we'll switch to green, and what green does is give us this position here. That's what we really want to look at. Let's get that black line out of the way so as not to confuse things. And here we have the utility with insurance. Okay, great, you can see that. So notice that the insurer, that person is actually better off this way. Notice that the consumer would even pay an actuarially unfair premium up to a point. They'd pay more because they moved from here to here, and so that's great for them. And so they'd even pay more to get that if it left them just as well off. Here they're better off with the insurance. But if they were indifferent, they would still buy. Great. Is that clear? I hope. And if it's not clear, take a look at the first problem I've given you on your homework assignment. The homework assignment, I think I'll start out and begin solving it just a little bit to give you an idea how to proceed with this. And the question the homework assignment asks you is it gives you this kind of a setup for a problem, but it gives you actual numbers. And I think that the numbers are you get a lottery with no insurance. You're given a utility function, problem one. This is problem one on the homework. Problem one for the homework gives us following information. Utility is equal to x to the 1/2. It's a von Neumann-Morgenstern utility function. So we'll say it's a von Neumann-Morgenstern expected utility maximizer. And our no insurance lottery is, we'll call it L1. L1 is equal to 49 and 100. So 100 is your wealth. If there's no accident, 49, that is a $51 of loss if you do have an accident. Of course, those are nice numbers since we're sticking them into the square root function there. And then the probability of an accident is 50%. So 1/2, I'll put the other 1/2 in, but it's not necessary. 1/3. Yeah, it's necessary. You can't add any better than that. All right, they should sum to 1. Good, great. And so what we can actually note is that given actuarial fairness, that lottery, well, we'll figure that out in a moment, but what's the utility if I have no insurance? The utility of that lottery would simply be equal to 1/2, and then it's 49 to the 1/2. That is that's the expected utility if there's a disaster, plus 1/2 times 100 to the 1/2. The expected utility if there's no accident, no disaster. And so that comes to 8.5, I think, if I've done it right. Should be. Because that should be 1/2 of 7 plus 1/2 of 10. Oh, it sounds like 8.5. Great. And so actuarial fairness would mean that this is by actuarial fairness. Would simply be that 1/2 of the loss, 51, would it be equal to 2550, okay? That's the expected loss, and that should also then be the expected indemnity, that is the expected the total premium that you would have to pay for that. Great, and so we can figure out what our utility with full insurance and an actuarially fair premium would be. Okay, we can lay that out. So then we can ask, what is the maximum that an insurer could charge? Okay, so first of all, those will be the steps that you'll need to take. I will want you to figure out what your utility would be with full insurance and an actuarially fair premium, and then also figure out what is the maximum an insurer could charge. And remember, the insurer can charge the maximum so long as it doesn't bring them down below 8.5 utils. Okay, great. All right, and in fact, graphically, it will be a point like, if this is the point with no insurance, that will tell me that distance right there is what I'll be looking for to find out what the maximum I could charge is. So I'll pull them down to that point. Great. And so solve that one. All right, good. And I've got all that written out here, but I think I will not, I think I will skip that because that's left as an exercise for you. All right, let's see. Next, let's treat this just a few more little complexity, little things we can add in. This has been a very simple problem so far. Full insurance, actuarial fairness implies full insurance. Well, what else? If you've purchased insurance, you know that there's often something called a deductible. What's a deductible for? Well, first of all, how would we incorporate a deductible into our model? Well, let's go ahead and do that and then talk about why we might have a deductible. So the utility that we'd get from the level of insurance would simply be equal to P times, make that a small u, the probability of our accident, times the utility that we get if there's an accident, which would be W minus L plus Q, because we got the indemnity, minus the cost of the insurance, minus the deductible, D. The deductible is an amount D, and that's paid only in the event of an accident. And then we have U, that's a much nicer marker, 1 minus P. Utility of W minus pi Q, which is where we have no accident, okay? So the deductible occurs only in the event of the fire or the accident. Great. Well, why do we have the deductible? And the answer is problem of moral hazard. And moral hazard is the following. Suppose that notice that with full insurance, the homeowner is indifferent between having an accident and not having an accident because they're just as well off. They'll always be at this point right here, right here with full insurance. Okay, no matter what happens. So they're indifferent between an accident and not an accident. Great. Suppose that indifference alters the person's behavior. And if it alters the person's behavior, then it alters the probability of an accident. Now, the insurance premium is calculated using the uninsured probabilities, but those will be incorrect because the person's behavior changes once they get insurance. And so the insurer's lottery itself has changed. So suppose without the insurance, we won't do too much of this mathematically right now. But suppose that I have a small problem for this on the homework. Suppose the following. Suppose that without insurance, the homeowner, took precautions costing an amount delta, little delta, okay? And that gave us the probability of an accident P. The probability of our fire. Great. But with insurance, the homeowner, she or he, stops spending delta because now they're indifferent between whether a fire occurs or not. And so the new probability of an accident, new probability of a fire, is P tilde greater than P. Great. And the wealth of the person, the starting wealth now is W tilde, which is equal to W plus that they were expending before. That is, they have changed their wealth over to here somehow. Great. Well, clearly, the insurer who is charging an actuarially fair premium, pi equals P, is now taking an expected loss, an ex-ante loss. So pi equals P gives you an ex-ante loss. Ex-ante before the fact, expected loss, because, well, for the obvious reason that they were earning zero profit before, and now they're charging too little. They're earning negative expected profit. What do you do? Well, the solution would be to charge a deductible, and that deductible would have to satisfy the following. This is the solution, and let's go ahead and clear this up. And I was about to write it in red, but I fear that doesn't show up well enough, so we'll simply say the deductible will be this. We want to make certain that we've satisfied the following. The insurer wants to satisfy the following condition. The probability of, W minus pi Q minus D plus 1 minus P W minus pi Q. So I've got my deductible in there, and I want to make certain that that is greater than, put the greater, I'll write it over here so I've got enough space. So it's greater than P tilde. You have W plus delta. That is that right there, W prime, or W tilde. That is to say, that deductible is big enough to make them continue to take the precautionary measure to avoid the problem. The homeowner can guarantee himself delta, but D has to be large enough that the additional risk of paying that deductible deters him from not taking precautions. Okay, so there's one way of dealing with it. And mathematically, we have no trouble incorporating the deductible into the insurance story. Other kinds of measures, and these were things that we did when I was working in crop insurance. You require certain actions. So for example, for automotive insurance, often there will be a requirement for anti-lock brakes or something like that. Maybe certain kinds of alarms put on a building for fire purposes, sprinkler systems and things for fires. In crop insurance, there was a stipulation that you always had to use, stipulation in the insurance that you had to employ good farm practices, which are basically defined by USDA. And you also call for inspections by adjusters. We also had some insurance programs that would have satellite imagery for fields to inspect them, things like that. And then there are some things that you just won't insure because they're too risky. So in crop insurance, any land that had been infected at one point with a fungus called Phytophthora, you can't insure that. It just won't be done. So great. The idea is to insure against risks and also to try to control for opportunistic behavior, moral hazard, opportunistic behavior on the behalf of the insured. Okay, kind of an amusing aside, at least to me. The economist Robert Murphy, who actually used to teach at Hillsdale College, he's done some pretty interesting things in Austrian economics, but he wrote a book on anarcho-capitalism, and his solution to make anarcho-capitalism work was that everybody would have to have insurance against their own bad behavior. And so criminals would carry insurance against their own criminal activities. If you're a criminal, what is the probability of you committing a crime? Well, let's put it this way. If you're intending to go out and commit a crime and buying insurance against that, you're going to just pay the full damages. It didn't seem like a very reasonable kind of insurance to me. But at any rate, this is the basic framework for insurance. And so next time what we'll do, we will proceed and we'll cover optimal contract theory. And for now, I think this is enough to get you through your homework assignment that I've given you. And so on that note, I wish you all a happy Thanksgiving, and we'll be back again soon.